Welcome to homework.
Okay, so in this circuit, we see that R3 and R4 are in parallel connection in the circuit, and R1 is in series with these two. Now, what happens is fro from R1, we have the total current I total that goes through, and then it gets divided into these two resistors because they're in parallel connection. And when the switch is closed, then we have another resistor which is in parallel connection with R3 and R4. So what happens is when a resistor is in parallel connection, the equivalent resistance is lowered. So so for parallel connection, equivalent resistance is lower than the individual R. And for series connection, it's the opposite. So here, the equivalent resistance is actually greater than the individual R. So since we're adding another resistor here, so our equivalent resistance is decreasing. Now, if the equivalent resistance is decreasing, so that means the equivalent resistance in this part is now lowered, and what that means is we'll have an increase in current because our R is decreased now. And since the R1 is in series with this V, there will be an increase in voltage here because again, like, we need to start with V here and we need to end up at 0 here so that the voltage drop is consistent. So the voltage will increase around this region, and then if we consider all the parts individually, uh, so around this part the voltage drop will decrease. So that means, and since it's a parallel connection, so at each node the voltage drop is same. But initially, since there were only two resistors, the value got decreased once we added the other one. That means the voltage drop will decrease once we add the third one. So that means altogether, from initial voltage of R3 and R4, it will decrease. And since R2 didn't have any voltage, once we connected it some voltage appeared here. So that means the voltage will increase around this region, and since this guy is in series, so voltage will increase here as well. So if we write that down, let me clear this part. So just give me 1 second. Okay. Uh, yeah. So in part A, voltage across this will increase. So we call it V1. So V1 will increase. And then we call the voltage across here V2. So V1 and V2 will increase. And V3 and V4 will decrease. V4 will decrease. And similarly, since by similar argument, we can say that the current from, in this case, the current will become something from 0, because when the switch was not connected, there were no current passing through it. So the current will increase here. And for this case, since the voltage increased, but our R is constant here, that means the current will increase as well. And by similar argument, in these two cases, since the voltage drop decreased, so our current will decrease as well. So I1 and I2 So these are the currents of this one and this one respectively will increase, and I3 and I4 will decrease. And for part C, when we want to know the power output, so what happens is, since there's an increase in current I1, and I1 is equal to the total current because this guy is in series connection with the battery, so let's call it I1 as well. So that means the total current drawn by this battery has increased, and since the voltage output is the same, or the battery that is connected is not changing, so that means, and since our current has increased, so our power will increase, because we know that power is voltage times the current, so our power output will increase. So we know power is V times I, and that will increase. Okay, now for the second part, uh, we are given some values, and we see that they all have the same resistance, and the battery is 22 volts. So we need to find the individual currents at across each resistor. So what we do here is, we see that R3 and R4 are in parallel and the switch is open, so that means we don't have to worry about R2. But then R1 is in series with R3 and R4. So what we do here is, first we need to find the equivalent resistance, and that is given by this formula where R1 is in series with these two guys, so that's why you're adding R1 to the equivalent resistance of R3 and R4. If we do that, we get some value like this. So that's the equivalent resistance, and if we draw diagram, it gives us something like this, where this is our V and this is the equivalent resistance. So if that's so, that means our total current will be the battery voltage over Req. So that's the V battery, and I total is going to be 22, which is the voltage of the battery, divided by this equivalent resistance, and that gives us this quantity, 0.09462 amps. And now why this is equal to I1? Because this resistor is in series connection with the battery, so that means the total current, as we mentioned, the total current flowing through R1 is same as I1, so that's why this is our I1. Now, to get the voltage drop, we have to use VI, which is equal to I1 times R1. This is using Ohm's law, and that will give us the voltage drop across R1. So that means if we know R1, we know the voltage drop across this part, and remember this switch is open, so that means there's no current passing through it. So voltage drop across this part only, R3 R4, and that's going to be the total voltage minus this V1, and that gives us 7.334 volts. And so if you want to calculate the current, since they're in parallel connection, so for 3 and 4 the voltage drop will be the same, so that's why we took this. And since R2 and R3 are same as well, so whatever current we get as I3, that's going to be equal to I4. So the final answer that we get here is, we divide our VP by 155 ohms, and that gives us an answer as 0.04732 amps. Okay, so this is our I3, I4, and this is our I1. Right, now we have to do the same calculation, but now we have another resistor. R2 is in series, so what we do here is we do the same calculation, but here we'll add an extra term, which is 1 over R2, because that's in series connection. So it's going to be R1 plus reciprocal of R2 plus R3 plus R4. And since we know that these values are all equal, we can plug in, and they're 155 ohms, so we can plug in the number and get our equivalent resistance as this. So as we can see that the resistance that we got here is higher than this. So that proves that if something is connected in series, that lowers the total resistance. So similar way, we find the total current, which is V battery divided by the equivalent resistance, and that will give us 22 volts divided by 206.7 ohms, which is going to be equal to 0.1064 amps, and that is equal to I1. Right. So once we know I1, we need to find the voltage drop, and then from there we get the voltage drop across the parallel resistors. So let's get onto it. So V1 equals I1 times R1, and I1 is this guy and R1 is 155, so it's going to be 1064 amps times 155 ohms, and that will give us 16.49 ohms. So the voltage drop Vp will be V battery minus V1, and which is 5.51 volts. So if we know Vp now, we can find out I3, I4, and in our case we can find I2 as well, because again the voltage drop is same there. And okay, so it's gonna be I3 or 4, because we don't have R2 connected. It's gonna be 3 or 4. So now I3 will be Vp divided by R3, which is equal to I2, which is equal to I4. And if we put the number, we see it's 5.51 volts. So 5.51 volts divided by R3, which is again 155 ohms, and that will give us a current as 0.0355 amps. So that means the prediction that we made in part B are all confirmed. So that's the three currents, I3, I2, and I4, and that's our I1. Thank you.